Hi, thank you so much. It's a real honor to be invited to speak at this conference. This work is the doctoral thesis of my student, Jacksyn Bakeberg, and the motivation for it is that I would say this is a kind of meditation on the problem of the Langlands correspondence. That's why we're here. We want the Langlands conjecture to be a theorem. And the current state of affairs seems to be that there are two constructions, at least, where we have, on the one hand, an association to every irreducible representation pi of a p-adic group. We have a phi pi. And I might call this the Fargues-Scholze construction. And another one, which I might call phi pi Galois, because Tasho gave his talk on Monday describing a kind of unique, if it exists, correspondence. And we want to know, do these things agree? And I think many people have various approaches to this problem, and just here's my own meditation on the problem. I want to reduce this to some formula that I will tell you about now. So let's start by talking about the Bernstein center. And this will include some previous work on this sort of problem. And the setup is going to be like this. As usual, F is going to be a p-adic field, a finite extension of QP. And then G over F is going to be a reductive group as usual. And the Bernstein center, I'm going to just write a Z of G. And this is defined to be the endomorphism algebra of the identity functor on the category of smooth representations of the group G of F. So how about that's rep smooth of G of F? Yeah, so it's something rather categorical and abstract. And if you have an element of this group, so by the way, the representations here are going to be complex, and I'll give you a heads up when I want to move from the complex field to the l-adic field. But for now, they're complex. And if you have an element of this Bernstein center, you can act it upon a representation pi, and if pi is irreducible, then Schur's lemma says that it has to act as a scalar. And no, this should be lambda into pi z. So its action should just act as a scalar on such a thing. So you get this kind of character from the Bernstein center towards the complex numbers for any pi. So I want to give you another description of this thing. So, it's kind of analogous to what you might do for representations of a Lie algebra. And in that case, you have a pretty simple description of what the Bernstein center is. It's related to the universal enveloping algebra of the Lie algebra. Just take the center of this, and that's your Bernstein center. But in the p-adic case, it's much more complicated. But we do have an explicit description for it. This is isomorphic to a certain space of distributions on the group G of F. I'm going to decorate distributions with the C for compactly supported, and then conjugation invariant. So the C here is some notion of compactness, and this means that if I have a distribution here, let's call it delta, and I convolve it with some compactly supported F, the result should also be compactly supported. So this is true for all F in the same space of compactly supported functions on the group. So the compactness means that it convolves compactly supported into compactly supported. And then the other condition is that it's conjugation invariant by G of F. All right. Well, whatever group I want, whatever I could place into this construction, but it's really not clear how to construct elements of this Z of G. All right, well, here are a few. Okay, so I'm going to move this up. Okay, I have to get used to the board mechanics. This one. So if I have this, why would I use the hook? People use the hook. I think they're impatient. Okay. Well, here's a really silly example. The Bernstein center is a unidal algebra, so it has a 1. But then on the other side, it should correspond to some distribution. So what distribution is it? It's the Dirac delta function at the origin of G. And let's just think about this for a second. The Dirac distribution is quite famously not a function. Some functions, a function, if it's integrable, gives you a distribution, but the Dirac delta is not. It is, however, a function when you're restricted to a dense open subset, namely elements which are not the identity. So just remember that pattern, yeah? Okay, B. This is a little less trivial. All right, so there's the paper of p-adic, which describes some elements of the Bernstein center. So, you know, Z of G, I can consider its spectrum, and this is going to decompose into blocks. You would call them Bernstein blocks. And let's say I have one of them. Let's call this omega. And this is going to be a Bernstein block. And they proved that the projector onto one of these factors corresponding to a Bernstein block, okay, well, that's going to be an element of this Z of G, so it's a distribution. So what properties does it have? It's locally L1. So that one actually is a function. And then here's another result about elements in the Bernstein center, which is a little more aligned with what we're about to do. This is a result of Varma. In the case of GL2. So in that case, we really do have a pretty unambiguous local Langlands correspondence. I'll call it pi goes to phi pi. Phi pi is going to be a two-dimensional representation of the Weil group. And then for each non-negative integer r, Varma computes a completely explicit expression for a distribution called ZR. So ZR is an element of the Bernstein center. And what does it do? Well, I can tell you what this element is by telling you what its character is. Oh, I wrote lambda there, so I better write lambda here too. Lambda pi of ZR. Now I'm supposed to give you a scalar. What scalar is it? It's going to depend on pi and also r. This is going to be the trace of a Frobenius element on some unramified Galois representation. Which one? How about I take phi pi, that's now valued in GL2. Then I take its rth symmetric power, it's valued in some higher GLR plus 1, yeah? And then that may be ramified, but I'm going to take its inertia invariance, and then now Frobenius is well defined on it, and I take the trace. So that's going to be a scalar. So this is hinting that if you kind of know the Langlands correspondence already, you can cook up various elements in this Bernstein center. I think Varma was interested in this one because of a relationship with vanishing cycles on the modular curve related to the Langlands-Kottwitz method. And so this is a little more related to what we want to do, except in this situation, I don't want to take inertia invariance, and I want to take traces of more general elements than this Frobenius. So far, so good. Okay. So the next thing would be excursions as studied by Fargues-Scholze. So let's review that. I will bring this one up. No, this one goes down. And then can I do them at the same time? No. No, all the speakers are like, no, you can't do that. Okay. Okay. Mm-hmm.
You got to flip with one hand.
Oh, smart. Okay. I'll do that next time. Great. And I can use the other boards too. All right. So, all All right, so this part is about excursions and the main result. So the work of Fargues-Scholze construct lots of elements in the Bernstein center in a way that's directly related to the local Langlands correspondence. So I'm going to just write this as exc with a script E, reserving Roman E for a different purpose. So the domain of this is going to be the coordinate ring of the stack par G. So this is supposed to be, well, we've used this before, so I don't have to write the definition, but par G is the stack of L parameters for the group G, and O is going to be functions on it. If I've got a function on this stack of parameters, then we get an element of the Bernstein center this way. So I'm going to write this as exc. So as an example of this, I'm going to consider data considered all the way back to Laforgue with excursion operators, but I'm just going to, for the purposes of convenience, just consider a certain kind of functions on here. So for all pairs, I'm going to consider a representation of the dual group, G hat, and I'm going to consider also just an element of WF, the V group. Then I can consider V tau to be an element of this thing in a way that I'll make clear to you in just a second. And then I'm going to say, okay, exc of this. Well, this is going to be an element in the Bernstein center. So this lives here. And what property does it have? So when I take its character associated to an irreducible representation, the result is a little similar to what I did way up there. It's going to be the trace of tau acting on something. And what is that something? Well, I can take the Fargues-Scholze parameter associated with Fs. So that's valued in the Langlands group. And then I can compose this with V to get an actual representation on a vector space. And now I can take the trace of that thing. So this thing is going to be really a function on the parameters. Yes, a function on the parameter space. If the input is phi, the output can be this. So I really get a function here. So I've now described for you as some element here by prescribing what its character is. So, I mean, the monumental work of Fargues-Scholze really shows that you have such a thing, and thereby links the representation of G with actual elements of the V group. Okay. So I might say this, that this exc is an encoding of the Fargues-Scholze correspondence, right? If you knew it in enough detail, you could reconstruct what pi goes to phi pi actually is. That's what Fargues-Scholze do. I mean, they follow the pattern of Laforgue to say, well, and by the way, they use way more general excursion data than this. You have some finite index set, and then you have as many elements as that of the V group, and then you have a representation of that many copies of G hat. That's the most general thing, but I'm not writing all that. I'm just writing pairs like so. Okay. Okay. And then, yeah, okay. I'm just using the linear algebra data that produces this for today's talk. Okay. Okay. I guess I'm ready for the theorem. Is that okay? All right. So I'm told I can write here, so that's great. So the theorem is about just the group SL2 for now. I'm going to also assume that P is not 2. And in this situation, it's known that, well, you know, the different constructions really all give the same thing. So I can really talk about the local Langlands correspondence. And then in this situation, G hat's going to be PGL2, and the construction requires a V. That's going to be a representation of this group. So how about the smallest one? How about GL3, the adjoint representation? That's going to be my V. So the theorem says that we have a completely explicit construction of what the excursion operator is as a distribution we want to talk about a particular distribution, so you want to know what it does on an arbitrary compactly supported smooth function. Well, Bakeberg's thesis tells you how to do this. Here's how. The theorem says there's a perfectly explicit sequence. I'm just going to call it E sub r, and E sub r depends on the pair v and tau, okay? And these are going to be smooth functions on the group G of f. And these satisfy what? All right, so there's going to be an A and a B. So there's a sequence of functions, so ER v tau, these actually converge to X v tau. Convergence in distribution. So what this means is when you take this function and convolve it with f, and then take the limit as r goes to infinity, what you get is that it converges to the convolution of this with f. So this completely describes what the excursion distribution is. Okay, maybe it's not so surprising that the thing exists, although it's impressive that we actually have a formula for it. So this really is a formula for what the distribution is. In the same way as, well, you can imagine some functions like bell curves which converge to the Dirac distribution. Okay, great. The part B is kind of the part with more content. It has to do with the pointwise distribution of this sequence. So part B will say, and I'll give more details in a second, on a dense open, and I'm going to call this dense open U v tau, and it lives inside of G of f, indicating that this is some kind of process that is more general than just this context. The sequence of functions ER v tau actually converges pointwise. It converges pointwise to a function, and I'm going to call this Roman exc of v tau. This function lives where? It lives in C infinity of G of f. It's a smooth function, and it's locally L1, so it's integrable locally. And this function I might call the excursion function. That's the title of the talk. And a function is more explicit, it's less data than a distribution. And I said that the distribution encodes the Langlands correspondence. So in a little, sort of weak sense, this function actually encodes the Langlands correspondence for the group SL2. And I can tell you exactly what it is. The formulas are sort of long, so I'm going to tell you a piece of what this is in a second. I have further information about this. This function, exc v tau, is valued in z, 1 over p. So this encoding of the Langlands correspondence is basically integral, indicating some connection with motivic something, something. Like there should be some motivic interpretation of this. You don't need p-adic coefficients to explain what this is. Sounds, yeah? Oh, you're right. I'm so sorry. Otherwise, that makes no sense. It should be U of v tau. Thank you. Great. Yeah. Okay, so you may be curious what this locus U of v tau is. And so this I can explain now, and I can explain it in some generality. So let's go back to the general case. I'm going to describe what I mean by collisions. So let's say G is general, and let's say some pair v comma tau is given. I want to explain to you what it means for an element G of f to live in the bad locus. In other words, the complement of that U of v tau in that context. I'm going to say that G and G of f collide. Well, actually, for simplicity, I'm going to assume that the G already lies in the regular semi-simple locus. And I don't expect the excursion function to be defined anywhere bigger than this. So I'm going to say that this G collides with v of tau when, and what possible relationship could there be between these three data, an element of the group, a representation of v dual, and an element of the V group? It's sort of the only thing you could possibly write down. Here it is. When there exists some finite extension, well, okay, there's a list of data here. There should exist some max torus S inside of G. I want it to be F rational. It should contain the element G. Okay, great. Furthermore, there should exist a weight. So the weight is going to be a, okay, let's see if I get this right. It's going to be a character of S, the Langlands dual of S. And that's going to be the same as a co-character of the S, the original S. And I want this to be defined. Okay, I want two things about this thing right away I'll write down. First of all, this chi, it's not just totally random. It should be a weight for S hat that's contained in V. So I'll write that this chi is a weight of V. And furthermore, when you consider it as a co-character of S, I want it to be irrational in here. So it's a co-character. It's a map from the multiplicative group into S. A priori, that's defined over an algebraic closure, but I want it to be defined over E. That E is this E now. Okay. Gosh, with all those conditions, what can I do now? Well, maybe the only thing that makes sense. I've got this tau now, right? The condition is that this tau belongs to the V group for this finite extension E. And, the V group of E is related to, no, not isomorphically. Well, it is when you take the abelianization or something and you complete here, but in any case, there's map like of class field theory here. So this tau, you can think of it as living in here. Let me write this as rho. And oh, what's the condition? I want chi of, oh yeah. So G, I think, lives in S. And so chi of rho of tau equals G. There you go. It's the only thing that could be. So this I'm going to call a collision when this happens. It isn't likely to happen. So you can imagine if I'm given a V and a tau, this condition describes a sort of small Zariski closed subset of G of F. So its complement is going to be of this collision locus is going to be this U of V tau that I described. So right now we have this theorem for SL2, but you maybe or you can already imagine what you expect to happen in general. Okay. Any questions so far? Okay. All right. Well, I have a lot to explain. Let's see. Oh, sorry. Rho is the map from class field theory. So I guess it lands at, yeah, I guess it maps from the abelianization of this. And I mean, I guess that maps into this kind of thing, but that doesn't matter for this statement. Yeah. That's a good question. What are the denominators? Well, we'll have a look at the formula, all right. It seems like they are unbounded in G. So it seems like I think the function's, but I'll write down the formula and I'll see if you have any impressions about it. Okay. So we've got that. All right, very good. So where do I write next? Okay, so I guess I started here, so I can erase here now. Okay, is it better to use this one or the wet one? I don't know. So the way that Bakeberg's calculation worked is that we started with some kind of a priori formula for what the excursions do, and that formula had nothing to do with the work of Fargues-Scholze. Instead, it was more like, well, given that you know a Langlands correspondence, write down the only thing that the excursion distribution could be. So here's how this works. I'm going to call this a formula for the excursion distribution, or a formula for x v tau, and I'll just leave to your imagination how this would work for a more general sort of excursion datum. So the key tool that we use here is the Plancherel formula for G. That's a sort of generalization of a Fourier transform, and once the thing is transformed, you know what the excursion distribution is supposed to do to it, and that suggests what the formula is. So let's say G over F is more general, and I'm going to write here, recall the Plancherel formula. So this is going to be for an arbitrary group now. I'm going to write temp of G for the set of tempered representations. So that's going to be all the irreducible constituents of those representations which are parabolically induced from discrete series representations. So if they have some connection to discrete series, then they're called tempered. So this is going to be an induced representation from a parabolic up to G of some representation sigma. The P here is decomposed in the usual way, where M is going to be a Levy subgroup. And sigma, I'm going to write this. It's part of the discrete series of M, the irreducible representations of M, like this. Essentially square integrable representations. And what's the Plancherel formula? It's a formula for what an arbitrary function is in terms of the tempered spectrum of G. So for all F living in here, like a test function, the formula says, yeah, I have a formula for f of 1 in terms of the tempered spectrum. You could get a formula for f of g just by applying the formula to a translative f. But here it is. It's going to be an integral over all representations in the tempered spectrum of the Harish-Chandra distribution of pi. That's this, theta pi of f times d mu of pi. Okay, so I have to explain some notation. I hope this is pretty well understood. If I have pi, then I can consider pi of f an operator on the vector space of pi, and that's a finite rank operator and has a trace. That's what this is. On the other hand, this d mu of pi suggests that there is actually a measure on temp of g, and there is. It's called the Plancherel measure. All right, but what is the Plancherel measure? So I'm going to give a it's known what it is, but I'm going to give a description that overlooks so many details, so many details, just focusing on the parts that matter. So what I'll say is this. There exists what I might call a naive measure. d pi on the set of tempered representations. And let's just go over what this might look like. A tempered representation, how do you construct it? Well, I tell you how to construct it right here. If I've got one, what are the rest of the representations that are in the same connected component? Like, what are the connected components of temp of G? If I'm starting from this, all I can do is take the sigma and twist it by an unramified character. So the connected component of this one, ind pg sigma, is the set of all ind pg sigma chi, where chi is an unramified character of the Levy subgroup M in question, right? You can take the sigma and twist it like this. Then you get all of the rest of the representations that live in the same connected component, and you can kind of see, okay, yeah, this is at least receiving a surjective map from this set. And this set right here, well, depending on what the rank of the split part of M is, it's basically just a complex torus. And that complex torus has a Haar measure on it. And I'm going to just write that d pi is going to be the Haar measure on this. And I want chi to be, oh, thank you so much. So it has to be, so why don't I write that it goes from M to S1 to get the desired result, because this whole story is about unitary representations. And okay, so no one's yet interrupted me with many corrections, so that's good. So, well, maybe you should, because this thing isn't always irreducible. It usually is, but sometimes it's not, and therefore this can't quite be the correct statement all the time. So there's various asterisks, and I'm just going to indicate them like so. There's also like this d pi maybe shouldn't be exactly the Haar measure. There maybe should be some normalization factor that depends on the sigma. So there's the d pi, the naive measure on the tempered dual of G, and then there's also this Plancherel measure. All right, well, how are they related? By the formal degree. So here comes that. Okay. All right, so let's get, I'll just start erasing here. So the two measures are related. By this, the Plancherel measure is equal to the naive measure times this function on measures, which you might call the formal degree. It really depends on the sigma, not the pi itself. So to every discrete series representation, there's this formal degree, which is maybe familiar to the representation theorists. It's just some integer. And this is the relationship. Okay, so given all this, I want to tell you how you would construct this excursion distribution in an ad hoc manner, not knowing anything about Fargues-Scholze. Here we go. So I'm going to have to assume, though, that we know the local Langlands correspondence. Let's say you know it in the way that Tasho's talk describes it. I'm just going to write here, assume the LLC. There's what? Okay, so I think you want me to write something like this here, like this times this. Okay, so rather than explain all that, yeah, okay, so it's totally true. Like this is as stated. This is a bit too naive. So you could maybe fold the j of sigma into the d pi, or I could say this d pi, it's a Haar measure. It's not the Haar. It's not the normalized Haar measure to be measure 1 on the whole thing, but it's a Haar measure. So I just need to fold in this. There's some formula for this. Oh, the j varies with the unwrap. Oh, right. Oh, so it doesn't actually depend on pi. Oh, thank you. It really should be j of pi like this. Okay, thank you for that. Okay, but okay, good. But it should be constant on L packets, right? That's important. Yes. Constant on L packets. So if it's constant on L packets, I want you to ignore it for now. Okay. Okay. So that's just I wanted to introduce this formal degree. So I'm going to assume the local Langlands correspondence. So that says what? So I've been using irreducible for this. I needed some notation for just all of the irreducible smooth representations of G of F. So that's as good a notation as any. So ir of G of F, what is it? So this should be in correspondence with a collection of pairs. And Tasho told me there's like a first name, last name for this. Wait, who is that due to? Wait, someone said, what, who? Oh, Witek Gan, okay, great, great. All right, so first the last name, this is a phi pi. And then the first name, so the phi pi is, as usual, a kind of L parameter valued in the Langlands dual group. And then the second thing is going to be the delta pi. So what are these things? So phi pi is going to be a representation of the V group cross SL2C into the Langlands dual group. And then the delta pi, well, it's going to be an irreducible representation of some group, which is essentially finite. You take the centralizer of the phi parameter, and then you take the pi 0 of this, and then this is an irreducible representation of that. So given a phi pi, there's finitely many of those delta pi's, and the delta pi is the first name of pi. Okay, already used up this chalk. Go. So now I can give you the definition. This is the ad hoc excursion distribution. That is, I'm going to construct for you an element of the Bernstein center. So it's going to be given, as usual, a pair via tau. So then I have to explain to you what this x v tau is. And so I define it by evaluating it on some test function f. So given the Plancherel formula, I want to tell you now a number like this. So I'm going to have to integrate over pi in the tempered dual of g. And then I just write down the same formula, but I give a weight for it. So I insert here the appropriate term. It's like the trace of tau on v compose phi pi. Yeah? And then I can write the rest of the formula. So here's theta pi of f d mu pi. Yeah. So I've written down some excursion distribution. There's also the Fargues-Scholze version. And in situations where the group is, what is it, well understood, is that the term of art? Then we maybe know that phi pi is the same whether it's the Fargues-Scholze one or the Galois one, and then you know the excursions are the same too. So the point of writing down this function is that you know what the corresponding character of this is on a particular pi. It's going to be this number that's inherent in this formula. But now I find this quite interesting. Now that maybe if you know enough about these quantities, theta pi f, then maybe you can figure out what the excursion distribution is. And that's again going to be an encoding of the Langlands correspondence. And if you take away one thing from the talk is that this encoding is sort of simpler, a simpler beast than knowing the individual formulas for the characters that go there. Okay, so the first thing I want to just convince you of is that actually this is a stable distribution. So I'm going to keep writing over here now. So I've written this formula here. Let's just kind of continue the formula over here. So I could write this as instead of an integral over pi, I want to group the pi's by their last name into their L packets, their families. So that's going to be an integral. Forgive me if I don't explain every detail here, but I'm integrating over a measure space that just lists all of the phis instead of the pi's. And then this term only depends on the phi, doesn't it? And then there's going to be some interior term that sums over the pi's in the L packet. That is the pi's whose phi pi is the given phi. And then I have to write, oh, it goes here. So the rest of the stuff, right? So there's going to be the theta, okay. So I'm going to kind of insert what's going on over here into the d mu, okay? So d mu of pi factors like this, and the important thing about this d pi is that it's really independent of phi. That is, it descends from the collection of pi's to the collection of phis. So I might as well just write d phi. The degree of pi, though, really depends on pi. It may be different across elements of the L packet. So I'm just going to reorganize this sum this way. You get the sum over all pi's of the formal degree of pi, times theta pi of f, this thing, and then here comes d phi, this thing. So I've now expressed this thing as an integral over the phis of some function. Okay, what is that function? All right, well, the degree of pi is here. I wanted to convince you that this was a stable distribution. And that's a question of knowing whether this function is this thing already is a stable distribution. And indeed, this would follow if you knew the formal degree conjecture, which is a theorem in a lot of cases. Wait, am I missing a page? Where's my missing page? Okay. Oh, no, I've got it. It's right here. So the stability of this, excursion distribution, x of v tau, would follow from what's known as the formal degree conjecture. Formal degree conjecture, what is that? Well, I'm going to omit all of the unnecessary details here and just leave the fact that the degree of pi is related to the dimension of this delta pi, this thing right here. The formal degree of pi is related up to some benign factor that's explicit, that only depends on phi, that's why I'm omitting it, equal to the dimension of this delta pi, the first name of pi. So the formal degree equals the dimension of delta pi. And so this, by the way, is a theorem of Bézard. Okay. Oh no. Let me see, my handwriting is so bad, and then I'm trying to. Yes. How do I spell? Yeah, oh God, it's so bad. Oh no. Oh, is this basically? Oh, it's a U. Oh, I got it basically right. Oh. B-A-U. B, oh, yeah, okay. Like that. Boz. Okay, Boz. Is that close enough? There's no.
No A at the beginning.
No A. Oh, B. Oh, B. Oh, yes. Will you accept my apology? Okay, I'm very sorry. It's spelling. Okay, this is a theorem for. Okay, for classical groups, yes? Okay. Okay. So I think of this as rather an important thing to know. Actually, in thinking about this project, I almost would go to the point of packaging this conjecture along with local Langlands. Like, you don't just know this thing about L packets, you should also know what these first names are in their dimensions. What would you get out of that? You would get that this term in the parentheses is supposed to be stable. Why is that? Because that term right there inside of the parentheses is now going to be the same as, up to some constant, that it's going to be the sum over the L packet of the dimension of delta pi times theta pi f. And this thing is called the stable distribution of the L packet. There you go, the thing that Tasha was mentioning. So packaged along with local Langlands, is, at least as Calathe envisions it, is that this thing should be a stable distribution. And in fact, there should be atomic stability. All of the stable distributions should be derivable from those, coming from phis, from L packets. Okay, good. Oh, yeah, okay, so stable, yeah, so stability is kind of invariance by not just g of f, which is pretty easy to see that it already is, but rather the algebraic closure, yeah. Okay. And, okay. I kind of owed you some formula, and all right, I may skip this. So if you went to Tasho's talk, then you know that he has a parametrization of a lot of these phees. They are given in terms of some data consisting of a torus and a character on that torus. And once you have that data, Tasho hands you a formula for what that distribution is. So once you know that, you plug it right into the formula up there, and then you try to compute. So that's what my student did. Okay, great. So maybe just skip to, because I'm ending at 5:30, yeah? Yeah. Okay. Yeah. Okay. Okay. So, I'll just say this. Galois has kind of a parametrizations. For at least a large part of all of the L parameters for a group G. And in some circumstances, you get all of them, especially if you assume the prime P is large enough relative to the group. In terms of some data, and what is the data? Well, I mean, the short of it is that it's a torus and a character on that torus. The details are, you have an algebraic torus, S over F, something abstract, but then part of the data is a stable conjugacy class of embeddings of S into the group G, where the image ends up being a max torus. So that's one half of the data. The other half is a character theta. The character theta is not quite a character of the group S of F, but rather of a certain double cover of it. And I can't explain how you get the double cover, but it's some process that's starting from S and it's embedding into G that gives you this. Tasho explains exactly how you construct a class in H2 of this group that tells you exactly what this double cover is. So the double cover, so this is mapping 2 to 1 on S of F. And this has to be what's known as a genuine character, in the sense that it does not factor through this. Yeah. Okay, fine. So you can express the entire excursion distribution, x v tau, because it's going to be given as a sum or an integral over all of the possible phees. You can now at least organize them into a sum first over the s's, and then an integral over the thetas. And in nice situations, this is going to be a compact group. Like if this is a compact group, then actually it's going to be a sum, not an integral. So I want to just express this as a sum over excursions, and now they're labeled by v taus like this. So this is where you just include the parameters that come from S. I've heard it referred to as the birth torus of phi. Every phi is born somewhere, it's born on S. So it's just organizing the sum this way. So if I'm going to give you a formula for the left, I should just give you a formula for the right, and I'm just going to give you the tiniest sample. So this is the case of SL2. So this is a new section, I guess. I want the S here to be non-split. I want the V. Well, this is a representation of PGL2. There's an adjoint representation, but actually I want to subtract 1 for this. For convenience purposes, that's actually a virtual representation, but you can still plug it into X. And, okay, I'll continue here. Oh, and also the p should not be equal to 2. Okay. All right. Oh, v, well, well, then you'd get a two-dimensional representation of PGL2, and there just isn't one. So, there's weight, it contains one as a weight. PGL, so this adjoint representation contains this character, its inverse, and also the identity as its weights, and I just want to get rid of that one weight. Is that right? Okay. So the terms with, yeah, very good. Yes, I just want to focus on the case of S non-split. Well, I already said that. Since it's non-split, what is the F rational points of S? You should get the norm 1 elements in some field E. So E over F is going to be quadratic. And in particular, this group is compact. And because of this, the set of characters on it is discrete. And that would be true for this double cover as well. And I want to give some kind of level function that tells you how far from the origin you are here, and I don't even want to explain exactly what it is. Let's just say the identity goes to infinity, and then all the other elements go to z at least 0. And the closer you are to the identity, the larger this number r is. So this r is a function on S of f, and you can also, I'm also going to use the same r to denote the level of a character, without even explaining exactly what I mean. So I can write this as x s of v tau. I can write this as a sum over all such r of some cutoff like this. So I'm just considering those characters which have level r. So that is, I'm kind of summing up all of the thetas, the characters that vanish on a certain locus. If it's level r, I'm just going to include them into that. So this is a way to organize that sum. So maybe now you can imagine how this calculation is going to work. You can organize, as if you know exactly what all of these S thetas are, if you have formulas for them, and you do, you borrow them from Tasha's work, and then you plug them in, and you try to execute a sum over all shells, like all characters of level exactly r. And then you see what you get. Well, here's what you get. Okay. Where did I write it down? Okay, great. So I have to tell you what tau is. I'm giving you kind of a sample of formula, so I'm going to make various assumptions. So the tau here lives in WF. Well, here's a quotient of WF. It's called the relative Weil group. You mod out WF by the commutator of WE inside of it. So it's this pretty classical thing. I just want to label what you get by tau E. That lives there. So this WEF, it's some relative Weil group. It is an extension of the Galois group by the units in E. And if I write this group as sigma, then, okay, I've got a tau E, I've got a sigma, I can apply sigma to elements of tau E. And when I divide tau E by its action by sigma, what I get is an element of E star. So in fact, it's going to be a norm 1 element. So I'm going to just let Z be the norm 1 element that I get. This lives in norm E1, and this is exactly S of F. So the point of this exercise was to start from tau and end up with an element of E, which is actually living in our torus. The other thing is that we've got group elements. I want to define for you an excursion function, and the function lives on the group. And I'm actually just going to assume that the element of the group is conjugate to an element of the same torus, and that's going to be the story. So I'm going to call down the first, this one. Nope, that one. Yeah, that's the one. All right, this is going to go up at the same time. Good. All right. Okay. All right, this is going to be a formula. Ooh. I'm going to assume an element of g of f actually lies in S of f, but doesn't collide with the pair v tau, in a sense. Collision would mean, if you really study what I meant by collision over there, you would find that a collision would mean that if you already assume G lies in the same torus, that is the burst torus, then G is equal to Z or Z inverse, because Z and Z inverse are like the weights that appear in this adjoint representation -1. See, that's why I got rid of the 1. So assuming no collision, I'm just going to tell you what the Roman X is. All right, so it's just the one coming from the burst torus S. There's other formulas for the other S's, and I'm also going to assume that E over F is unramified. I forgot to assume this. See, it's just a little piece of a piece of a piece of Bakeberg's set of formulas. Here it comes. Q to the minus R of G times 2 minus Q plus Q. By the way, Q is just Q squared minus 1, and lowercase q is the size of the residue field, times negative Q to the 2R Z G inverse plus, again with this Q, sum R equals 1 to R of Z of G inverse minus 1 of simply Q to the 2R plus 1. Ooh, that's it. Wow. It's just the geometric series going on over here. Well, what do we observe about this formula? First of all, it's rational. In fact, it's integral once you invert p. Jean-Francois's question was something about denominators. Well, there's the denominator. I would say it's unbounded. It depends on where g is. But it doesn't depend on tau, though. And what you see here is a sum where the sum is indexed by r's that go up to zg inverse. So the closer that z gets to g, oh gosh, there's another assumption. I'm going to assume one other thing, which is that the z and the g are congruent mod whatever the uniformizer of pi is. There you go. There's different formulas if you don't assume that. Lowercase q is the size of the residue field of lowercase f. Lowercase f. So q squared would be for e, yeah? So the closer that this z gets to g, the more terms there are here, and then this sum blows up. But if it's not, then it kind of cuts off at some situation there. Okay, so I guess I should really stop soon, right? Oh, well, I had a whole section I was going to cut, but if I have 5 minutes, I can tell you about speculation. I mean, the reason I am interested in a kind of connection between this and geometry, and that connection is really unclear right now. But since you see before you a rational number, I think, at least the numerator of it should be counting something. Counting what? Fixed points. I think this should be a fixed point formula. So that's one kind of motivation for doing this. If you magically found a fixed point formula that produced this, then you would have shown that Langlands correspondence is the correct one, that you have the right encoding. And the situation where I know something might be something like a case of GLN or PGLN. So this section is called speculation. About the geometric significance of this. So let's consider the case where G is the group PGLN, and G hat is the group SLN. See? And in this situation, V is the standard representation of that SLN. So under these circumstances, okay, well, there's a whole machine that produces spaces of Stukas for you. I want to consider the situation where you've got the group is G, the B here is the kind of slope 1 over n isocrystal, and the V here is going to be that V. So there's a G, a B, and a V. There it is. So this I'll just abbreviate as a Stuka space. It's going to be the infinite level Stuka space, and it goes by another name in this situation. This is the Lubin-Tate Tower at infinite level, a real object that I like a lot. And I have a little proposition for you. Let's say I have a test function, C infinity G of f. The cusp means that it's only supported on the cuspidal part of the dual of G. That makes my formula a lot easier. And tau, let's say this lives in the V group of F. Then this excursion, x of V tau, we can hit it on with the test function f. And what's the relationship to geometry? Well, it appears inside of the cohomology of this Stuka space. So what I can do is take the trace of not just f by itself, but the trace of f comma tau, acting on what? The compactly supported cohomology of this Stuka space, like this one. So the reason this works is that we have some knowledge about what this cohomology is due to Harris-Taylor and Scholze, right? So here's the one-line proof of this, which is just that the cuspidal part of this cohomology is known. The result of Harris-Taylor says that this is a sum over the cuspidal representations of pi. It gets tensored with phi pi. This is the local Langlands correspondent of pi, but then there's this other group that shows up, and that other group gives you a representation pi b. That's the Jacquet-Langlands correspondence. But I don't care about that group so much, I just care about the dimension of this space. So that's going to be the dimension of pi b. Well, guess what? The dimension of pi b, that's a finite dimensional representation of an essentially compact group. It's the same as the formal degree of pi. So you get this sum with weights degree of pi. And then the rest is definitions. If you try to integrate f tau, you take the trace of f tau on this, you get the excursion function that I wrote down. Here's where the formal degree appears. So that's my one-line proof of that. Okay, great. All right, so what's the point of this kind of thing? Well, my point I want to stress to you is that the excursion distribution should really be related to the trace of such pairs acting on the cohomology of, well, local Shimura varieties, yeah? Oh yeah, it's too far for me to get it. Okay. So if you wanted to turn this from a statement about distributions to a statement about functions, you should replace the test function f with an element g and ask, does that make sense? Can I take the trace of a pair g comma tau on the cohomology of Stuka spaces? I'll go very fast, I'm sorry. The function, okay, that's Roman exc of v comma tau. Okay, I should allow this to be here, and there should be no collision. This should be the trace of G tau, the pair. That acts on the cohomology of this Stuka space. So this should converge. Should converge. You know, this is an infinite dimensional space. If I have an operator on an infinite dimensional space, there's no guarantee that it should have finite rank and so that its trace should converge, but in this case it does. So I'll tell you why it does. Here's why. Okay, within the Stuka space, there's something called a special locus. The Stuka space is the moduli space for Stukas, or you can think of them in terms of p-divisible groups or formal groups in this case. Sometimes they have extra endomorphisms, and that's called special. NSP means not special, so that's the dense open locus. So this is inside of here. I'm going to combine a few facts about this. The pair G comma tau fixes no points at the boundary of this. So it turns out that the special locus, if you're fixed by a point G comma tau, if you have a special point and it's fixed by G tau, that means that G and tau collide in this circumstance. So if G does not collide with V tau, then G tau doesn't fix anything special. So it doesn't fix the boundary of this. The Stuka space itself also has a boundary, but there's other reasons why G tau shouldn't fix them, related to G being a regular semisimple, which I'm assuming. And then the last thing I'm going to write is that we know something about the space of Stukas for the group PGLN. When you remove the special locus, this is cohomologically smooth in the sense of Scholze. And that's the result of Alexander Ivanov and myself. And what it means is, well, among other things, what it means is, if you look at a compact, a quasi-compact cohomologically smooth space, a perfectoid space, the cohomology of it is finite dimensional. So this non-special locus is exhausted by quasi-compact subsets. The cohomology of each of them is finite. And as you go out to the boundary, the pair doesn't fix any of them. So those facts together show you why this converges. So there's a geometric reason why you should expect this excursion function, not distribution, to exist. If you can get this to work in a big matter of generality, and if you can somehow make a formula like Bakeberg's appear by counting fixed points, then you will have proved that the two Langlands correspondences are the same. Thanks so much.